Hello, my name is Edson Rangel, and these are my teammates, Vizconde and Saul Hernandez. We are Los Troncos. This is Project 2 Finite Element Analysis. The problem that we were tasked to solve is to find which bolt size and material combination has the highest stiffness and lowest stress on the top plate, and also which system has the highest safety factor. We were assigned 3 different size screws, which consist of a 1/4 of an inch, 3/8 of an inch, and 1/2 of an inch screws, which we split evenly amongst the 3 of us. We use SolidWorks to make a 3D model of the joint system. The joint system consists of a bolt, 2 washers, 2 plates, and a hex nut. The bolt, the washers, and the hex nut were provided to us. As to where the plates, each member had to create their own plate based on the size of their assigned screw. After having all of the parts, we put everything into an assembly to create the joint system. Once we had the joint system, we threw it into ANSYS. ANSYS is a structural FEA analysis software used to run simulations for product design, testing, and operations. This software uses computer-based numerical techniques to solve physics problems. For our purposes of this project, we used ANSYS to run FEA simulations to compare the performance of the 3 bolts and their joint systems. As a team, we ran a total of 20 different simulations, in which 18 were split evenly between the 3 of us, and the last 2 were performed as a team.
Our next step is to run our simulations. For this example, we're using the 1/2-inch head screw bolt jointed system. Our boundary conditions are a fixed bottom plate, shear force on top face of the top plate, and compressive force on the top face of the washer. The shear force is 911.23 psi, and the compressive force is 6,536.1 pounds. The plate material for this simulation was aluminum alloy. These are the steps we took in order to run these simulations. These steps were taken from our in-lab assignments because this best describes how we run these simulations. So first, we open up ANSYS Workbench, select Static Structural, and on Geometry, we right-click, Import Geometry, and select our assembly that we created on SolidWorks. Next, we right-click on Model and select Edit. Then, on this window is where we can run our simulation. Under Geometry, we select our 2 plates and change their material to aluminum alloy. Next, we right-click on Mesh and select Generate Mesh. Now, to enter our boundary conditions, we right-click on Static Structural and insert Fixed Support for the bottom plate. Next, select Force and apply the force on the top face of the washer. Next, select Pressure and apply it to the top face of the top plate on the X direction. Now, in order to get solutions, we right-click on Solution and select Total Deformation and Equivalent Stress. Next, we right-click on Solutions again and press Solve. This will give us our results for total deformation and equivalent stress. This process was repeated for all 20 simulations. Each team member ran their simulations with their respective head screw size. For simulations 19 and 20, the same process was repeated, but we changed the resolution. Under Mesh, we lowered the resolution. We noticed that this also changed the number of nodes. Now, my partner Ben will discuss the results and the effect that changing the resolution had on our simulation.
Hey guys, my name is Ben Vizconde. Today I'll be going over our results and how we analyze each of those 20 different simulations. So with each of the simulations, 4 main things we're looking at being stress, deformation, safety factor, and stiffness. So stress and deformation were found the same way by inputting solutions into ANSYS. After running the simulation, ANSYS generated a plot and table where we could get our values from, basically our averages, maximums, minimums, and tabulate our data from there. Safety factor, what you're going to have to do is put a stress tool into your stress solution. And after running the simulation again, you'll be able to click into that tool and it'll analyze your minimum safety factor. Stiffness, what you're going to do is you're going to take data from the stress and deformation. You're going to create a load versus displacement graph. And once you take the slope of that, that'll be your stiffness value right there. So after running the simulations, ANSYS will animate it for you as well, just so you can see what's visually going on based on this YouTube video right here. So right here we have our 9 simulations. The first ones we ran for the aluminum plate. So we ran 3 different types, being our compressive, shear, and then both compressive and shear. But for each of these, the half-inch always beat out the other 2 by having the least average stress, highest stiffness, and highest safety factor. So these are the graphs I mentioned before about the load versus displacement. This is how you're going to get your stiffness value. And for the second part of the lab, we had to run the same 9 simulations with the same boundary conditions. However, this time we would be using a copper plate as the material just to see how material would affect our results. But even when we changed the material, it was still seen that the half-inch screw had the lowest average stress while also having the highest stiffness and highest safety factor regardless of the loading. These are the graphs that we used to determine the stiffness for the copper as well. And for the third part of the lab, what we had to do is we had to compare our resolution settings. So the resolution settings has a lot to do with the nodes, and basically just the more nodes, the more data points that ANSYS can get its data from. So we tried out 3 different levels: coarse, medium, and fine. Coarse being resolution 1, medium being resolution 2, and fine being the 3rd resolution. So with each of these, what we expected is having our data converge to a set data point. Just because, but as you have more of the nodes and more data points to take from, the data should be converging and you should be reaching a flat out answer. However, since it was the medium, since it decreased and then increased, we were a little confused. However, that's just because the TA explained that since we're only using resolution 3, that the window for that randomness is still really big. So by having a resolution 4 or 5 or 6, you would get that flat out line where your data would be converging to an endpoint or the more accurate data that you're looking for. So really what we were able to determine is that the higher the resolution, the more accurate your data will be, as well as the half screw being the best. But with this in mind, you don't want to set your resolution all the way up to 7 or the max resolution, just because it'll take so much time to complete your analysis and your calculations, and rather the 4 or the 5 level will suffice and you'll get your accurate data from there.
After completing this project, the team determined that the 1/2-inch bolt was the best. After analyzing 20 different simulations, it can be seen that the 1/2-inch bolt minimizes the stress on the top plates and has the highest safety factor all throughout. No matter the material on the plates, the 1/2-inch bolt was consistently the best bolt in the joint system, beating out the other 2 bolts. In some simulations, the 1/4-inch bolt came very close to the 1/2, but at the end, the 1/2-inch bolt always ended up on top. The biggest takeaway of this project was that we learned how to use ANSYS to run simulations. For all 3 of us, this was the first time we used ANSYS for our project or for any other reason. And we learned how to analyze and interpret deformation and shear stress to determine the best joint system. From the last 2 simulations, we also learned how changing the number of nodes affects the safety factor and the average stress. We also learned how to find the stiffness of the bolt for maximum stress and the total deformation. After running the simulations, we came up with 2 different graphs, which were the maximum stress and the total deformation. We threw them into an Excel file, and we looked at the slope of the graph to determine the stiffness of the joint system. This was a very interesting project, which required a lot of time. The first milestone was probably the toughest one, just because we were new to the software and we didn't really know what to expect. We had done similar work in previous labs, but it was still something new to us, and that's why it took the longest. And for the second milestone, we were pretty much doing the same thing, just using different materials, which facilitated the process. And for the last milestone, we also did the same thing as the previous ones. The only thing that was changed was the resolution, the number of nodes, and to see how that affected the factor of safety. And as mentioned before, increasing the resolution will give the best results, and that was found through the last 2 simulations. Thank you for watching.